Well, your daddy's got a new job and the bills are rolling in, and you're moving away to where the sun is always bright, and you're the talk of many parties, and you're the toast of all your friends, and you're so happy you just wanna break down and cry. And I wonder how Clinton's daughter feels today, yeah. They've asked about her daddy's job, what do you think she'd say? She seemed upset on MTV, what did Washington take away? I hope Chelsea's got a reason to smile today. I hope Chelsea's got a reason to smile today. Do you remember the day it happened? Or were you in the backyard? Hey, did your day leave something yet to be desired? And had you had a talk with mommy about who your true friends are? And were you happy to know that title George got fired? And I wonder how Clinton's daughter feels today, yeah. They've asked about her daddy's job, what do you think she'd say? She seemed upset on MTV, what did Washington take away? I hope Chelsea's got a reason to smile today. I hope Chelsea's got a reason to smile today. Well, I think about you now and then, I just thought you'd like to know. Hey, someone out there's hoping that you feel alright. And I imagine that when we're locked behind glass, things might get pretty slow, so you can take these words to bed with you in night. And I wonder how Clinton's daughter feels today, yeah. They've asked about her daddy's job, what do you think she'd say? Well, she seemed upset on MTV, what did Washington take away? I hope Chelsea's got a reason to smile today. I hope Chelsea's got a reason to smile today. Hey, I hope that Chelsea's got a reason to smile today.
So today we're going to be starting on the next topic, which is arrays and collections. Arrays are in both languages. Collections are something that are just in Java, but you should highly prefer them to use them over traditional arrays, and I'm going to show you why as we move along here. But of course, we're going to remember that we are on Piazza, we are on YouTube, so if you have any questions, go ahead and post there. Otherwise, you have already seen arrays implicitly. Many of you have some background already, so you understand what arrays are. We're going to get into it a little bit more depth here, though. It's rare to only deal with one number, right, or one character, or one piece of data. Instead, you need entire collections of data, and the way that you store those is through either an array or in a collection of some sort. Both of those languages use arrays, which are contiguously allocated pieces of memory. So here is my first visualization of it. And you've seen it all before because you've used argv at least. Argv sub 0, that's where the first one is. Remember that it uses 0 indexing. Argv sub 1, that's where the second argument is, etc. And so it's all contiguous in that the first element is right after the next element, or the second element is right after the first element in memory. There are no gaps. There are no gaps in the memory. Here's a chunk of memory, and then right after that is the next element, and the entire array is stored in memory all together. Right? The 0 index here refers to the first element, so there's contents in that array. This 1 goes to 3, or goes to the second element, et cetera, et cetera, et cetera. So if I have 10 elements here, then where is the last index? At 9. Because you start at 0, you're necessarily going to end at n minus 1 in general if you've got n elements. Okay? The way that you access those is by indexing. You use the square bracket notation, and then you provide the index at which you want to find the element. You can set the element, you can get the element, you can do whatever you want with the element once you've indexed it properly. Is this large enough for everybody in the back? Okay, good. All right. Otherwise, so let's go ahead and get into it with C, first of all. And C supports static arrays, okay? And it's not something that you want to use in practice, but it is a good way to get started. Static arrays are arrays that are allocated on the stack, right? Remember the call stack? The call stack is you've got function, calling function, calling function, calling function. Each one of these things is a stack frame. And so a static array is an array that is allocated right on that stack. For example, let me go ahead and give you the syntax here. If you just want to create an array, say, of 5 integers, you can use something like this. We'll make this a little bit bigger so I can see it. Right? You might be able to see it back there, but I have a hard time because the resolution on this one is terrible. All right, so I've created an array that can hold 5 integers. So obviously the indexing would be 0, 1, 2, 3, 4, right? The 4 would be the last index. And here I'm just doing what's called an idiomatic for loop to iterate over those elements. For I being 0, I is strictly less than the size of the array, I++. That is so common that we say that it's an idiomatic for loop for an array. Why a for loop, by the way? Why not a while loop? Does that seem... Yeah, it has a set length, right? The array has 5 elements. If you want to iterate over all the elements in an array, then you know up front how many iterations you're going to go through. You could use a while loop, right? And I'm not going to say don't do that, but it just looks weird, right? Because a while loop is usually used in situations where you don't know up front how many iterations you're going to go, okay? And all we're doing is setting the element here, right? That is allocated on the stack, okay? So if I were to visualize this with the Python tutor or whatever, Python tutor, right? There we go. I'm going to grab this code and visualize it over here. Hopefully it doesn't take too long. You'll see that these are allocated in the stack, and here is the main. And as I iterate over this, of course, I'm setting each one of these elements to 1, 2, 3, 4, 5, and it's done. Now, this is only one function, but if I were to do this in another function, say called foo, and I would return back to the main, what would happen to this stack frame right here? Remember when you function calls function calls function, how do you reverse that process? You take the stack frame off, you take the stack frame off, you take the stack frame off. So what happens to that stack frame when I return? It gets destroyed. So stacks are very limited in that you would not be able to create an array and then return an array back to the calling function. Okay. Here, let me demonstrate what I mean by that. Let's edit this code. All right. So I'll put another function in here. Create here void create array, and I'll do that stuff in here instead of over here, and I'll say create array. There we go. Let's visualize this execution. Main is going to end up calling this function, right? And you see inside this function that the array is created. So I create it, I set it 1, 2, 3, 4, 5, And suppose that I wanted to actually return this. Could I? What's going to happen when I return out of this function? Bye-bye. It got destroyed. So you're not able to return static arrays in C. Right? So that's one limitation. Since arrays are allocated on the stack, those stack frames are destroyed when the function returns. They're gone. They're lost forever. Also, another issue. The stack size is very limited. Right? In fact, I can show you how limited. I'm going to go into the CS50 IDE here, and I'm going to show you the user limits. All of them. Right? So here are all the user limits that you're faced with when you get onto the CS50 IDE. And by the way, these are standard. Right? So the core file size, there is no limit. You can have arbitrarily large files. Data segment size, unlimited. Ooh, cool. Nice. Files, oh no, here's an individual file size. I believe that those are kilobytes. So that would be 500 gig, I think. I'm not sure. But let's go ahead and come down here to the stack size. Those are kilobytes. 10,000 kilobytes. Translate that to megabytes. 10 megabytes. So could I create a static array, could I create a static array with 10 million elements? Let's find out. Here we go. I'll cut and paste this. Instead of 5, let's go with 10 million. 1, 2, 3, 1, 2, 3. Oh, no, that's too much. 10, 1, 2, 3, 1, 2, 3. There we go. I think that's right. Anyway, how much memory am I asking to put onto this stack, the call stack? 10 million integers. How many bytes does an integer take? 4. So 40 million bytes is how many megs, roughly? 40 megs, right? That is 4 times the stack limit size. Let's find out what happens. And of course, you need to do something with it so that it doesn't get compiled away. GCC, oh, I need to go into honors, GCC, demo. What do you think is going to happen? 10 million integers is not that big, by the way. 40 megabytes, you have that, you have like orders of magnitude more memory on a typical memory stick, right? 40 megabytes is nothing. But what's going to happen? What happens when you stack dishes too high? They'll fall, right? They'll overflow, right? Stack overflow. And I get a segmentation fault out of that. You tried to put 40 megabytes onto a stack that was limited to 10 megabytes. You can't do that, right? So the stack space is limited. What do we need to do instead of, here, I'll even put that over here, right? You can use this ulimit to find out what it is. 8 megabytes is what it was last year, so I'll go ahead and change it to 10 megabytes there, right? Apparently they upped it for some reason. Allocating even moderately large arrays is not even going to be possible using static arrays. In Java, static arrays aren't even a thing. They do not have static arrays, okay? So how do we go about solving this problem in both C and in Java? We use dynamic arrays. Dynamic arrays are different than static arrays because they are allocated elsewhere in memory. Dynamic arrays are allocated on the heap. Right? What is a heap? All right, so again, this is a metaphor, right? Think about a stack. When you think about a stack of dishes, it's very nicely organized, right? There's the first dish and the second dish, the third dish, the last dish, the topmost dish, right? If you just stacked your dishes in a big giant pile, that would not be organized, right? So a stack in this metaphor is a very highly organized piece of memory. What about a heap? When you think about the word heap, what comes to your mind? A chaos, okay. A heap of stuff, right? A heap of crap. You come home, like a heap of clothes, right? You take off the dirty clothes and you just throw them on top of the heap, right? Is there any organization to that at all? Nope. So heaps are much larger though, right? That heap of dirty clothes is much larger than your stack of dishes could ever hope to be. So the heap is a much larger but less organized chunk of memory. And when I say less organized, of course it's still memory, so it's highly organized, but it's not it doesn't fall to you to make sure that everything is contiguous. It falls to the operating system. That's the operating system's responsibility to make sure that that chaos is managed. I like that word, chaos, right? So in C, you allocate memory on the heap by asking the operating system for it. You go to the operating system and you ask, I need enough memory to hold 10 million integers. Right? And the way that you do that is by using the memory allocation function. Right? I'm going to cut and paste this because it is, I bold these things. The memory allocation function is the malloc function. Right? And it has the following signature. Right? So a couple of new concepts here. What is its return type, first of all? Void star. Right? It's not a void function that doesn't return anything because you are asking it for memory. And malloc is going to say, okay, I'm going to go to the operating system. Here's the memory you asked for, and it delivers you the memory. Right? It needs to give you some pointer to that memory. But what is a void pointer? Now, it only takes one argument, right? The size of t. I wonder what that is. What do you think size stands for? The size or the length of the, carefully, the dynamically allocated array, right? More than that, it's actually a raw size. It is a number of bytes, all right? So let's go ahead and go over each one of these in detail. Void star is what's called a generic void pointer. It can point to anything, right? So remember when we were looking at pointers here, int star, what kind of pointer is that? It's an integer pointer. It's a pointer that can point to an integer. What about double star? What kind of pointer is that? It's a pointer that can point to a double, right? So what does void star mean? Does it point to nothing? What's the pointer that points to nothing? Null, right? This is a different type of nothing, right? Some years ago, I had a student in the VR course that they made a video game and they called it Call of the Void. And I pointed out, wait a second, a void can't call. A void is nothing, right? It was just a joke, but void is another idea of nothing. But it's a void. It's a big hole. Well, you can put whatever you want into that hole. You can throw all the garbage that you want into that hole. Void is a pointer that can point to anything, right? A void pointer can point to any type of data, right? So why does it return a void pointer? If malloc returned a specific type of pointer, we would need 50 different versions of malloc. Right? We would need a malloc for integers. Right? We would need a malloc for doubles, etc. And when we create our own types of variables, we would need a malloc for that new type of variable. For example, later on we'll look at creating structures. If I create a structure that represents a student, I would need yet a new malloc to create a student instance. Right? Do you want to go down that route of having 50 different functions that all do the same thing? It just returns a different type of pointer? No. And so they didn't either. They said, we're going to have one function that simply gives you a chunk of memory. Whatever you choose to do with that chunk of memory, that's your business. If you want to treat them as a bunch of integers, that's on you. If you want to treat them as a bunch of doubles, that's on you too. Right? You can treat it however you want. It's just a chunk of memory. And for that reason, we have to tell it exactly how many bytes we want. Right? Size t can simply be thought of as an integer, right, representing the number of bytes you are requesting. Right? So, for example, if I wanted 10 million integers, how many bytes does an integer take? 4. So 10 million times 4, 40 million, right? That would be one way of doing it. But if I wanted 10 million doubles, how many bytes does a double take? 8. So I would need 80 million bytes, right? It's not a good idea to hard code those values, right? You can use the size of macro. It is a macro, it's not a function. It looks like a function, but it's not. But you can treat it like a function. You can use the size of macro to determine how many bytes each type takes. For example, you can use size of int. And generally that will end up being a value of 4 because there are 4 bytes on most systems. Now, it's not necessarily the case all the time. There have been systems that, in fact, the C standard only says that an integer has to be at least 2 bytes, at least 2 bytes. There have been systems where an integer ends up being 3 bytes. There have been systems where an integer ends up being 5 bytes. Right? Those are very niche, weird systems that you'll probably never deal with in your entire life. But imagine that you could go over to a new system where integers are much larger, and now they're 8 bytes. If you had hard-coded 4, you would have to go back and change your code. Whereas if you used size of int, that's always going to be right regardless of what system it's on. How do I get the number of bytes of a double? Size of double. Right? Double, you got to spell it right though. There we go. All right. So let's bring this all together in an example here. So remember that this was resulting in a segmentation fault. You can't do this. Right? Let's go ahead and change it now so that I'm using malloc instead. The first thing I'm going to do is what's called bookkeeping. I'm going to put that 10 million over here into another variable. Because in C, you have to do all of your bookkeeping. In C, there is no way, once you create an array, there's no way to ask C, how big was that array? In Java, it's different. Java stores the array in this .length property, if you're familiar with that. But in C, there is no way. You have to do your own bookkeeping. Bookkeeping like accounting. How big did I make this array? Okay, I need to keep that into a variable. And if I ever give this array to another function so that it can do something with it, I also need to tell it how big it is. Right? That's just because C requires you to do your own bookkeeping. Right? All right, let's go ahead and change this. What I'm going to do is I'm going to change this into a pointer. Right? And we'll understand that, this with another visualization here in a second. All right? And we're going to make a call to malloc. Okay? So the first thing I want to observe is, what is my input to malloc? Malloc is, you tell malloc exactly how many bytes you want. So do I want 40, 1, 2, 3, 1, 2, 3. Do I want 40 million bytes? Well, yes, technically I do. But that's not the way that you should write it. Right? Do I want n bytes? No, I want n integers. So size of it, if I did it with 4, of course, that would not be best practice because I'm not making my code interoperable. So times size of int. Right? Now, n, 10 million, times size of however many integers you want, 4, that gives you exactly the amount of memory that you need. Now here's an under the hood kind of thing. Memory is, if you asked for 1 byte, right, that's small change, that's chump change. An operating system is not going to waste its time by just reserving this 1 byte of memory for your program. Generally, what's going to happen is that memory is separated into segments. Where have we heard that term before? Segmentation fault. This is a segment of memory that I'm going to go ahead and give to you. Generally, they're about 1 kilobyte, maybe 4 kilobytes or something like that. So if I ask for, say, 1 byte, it's going to end up giving me a full segment because it's inefficient to just give you this 1 byte and do all the bookkeeping and maintenance required to say that, well, these other 1,023 bytes are unallocated. You can go ahead and use them for whatever, right? It's just going to give you this chunk that is at least as big as you ask for, all right? That's just a technical under the hood detail, okay? So now what does malloc return here? Remember that it returns a void pointer. This is not correct syntax. I'm just reminding you that it returns a void pointer. Now, on the left-hand side, I've got an integer pointer. On the right-hand side, I've got a void pointer. How can I reconcile these two differences? Well, let's remember how to do this with simple arithmetic. If I've got a double C is equal to 10 divided by 20, is that going to end up being a double? Or what value will C end up having here? 0.5? Well, 10 divided by 20 is definitely 0.5, and that's what I want it to have. But 10 divided by 20, integer divided by integer, it's going to end up being 0. So how do I force at least one of these things to become a double so that it does end up as 0.5? 0.0 at the end, or alternatively, if it were a variable instead, I could do a typecast as a double. Good, typecast, remember? So I'm forcing B to become a double temporarily. I want to force this pointer to become an integer pointer. How can I do that? Do a cast, right? Just as I did down here. Yeah?
You have to cast the in pointer. Like you can't cast just in, correct?
Correct. Because now the left-hand side is a pointer, the right-hand side is just a number, right? And that ain't going to work. Because malloc is actually going to return a memory address, and if you treat that as a number, I take this back. 90% of the time this will work. It's not what you want to do, though. What's going to happen? Memory is much larger than a 32-bit integer. The memory addressing is done, like when we say like an 8-bit system, a 16-bit system, a 64-bit system, that's referring to the memory addressing. And so I'm 99% sure that this is a 64-bit addressing system because it has so much memory available to it. And if you're treating a 64-bit and shoving it into a 32-bit number, you are going to lose half of it, and therefore you're going to be mapping to some other memory low-order memory location that probably doesn't belong to you. So in any 64-bit system, that's probably going to fail. 32-bit system, you might get away with it. Don't do it though. Okay, so let me go ahead and recompile this and see if it works now. Right? 10 million takes a while, but hey, I went through. Right? I went through every single one and set it equal to 1, 2, 3, 4, 5, 6, all the way up to 10 million. Okay, it worked, right? And that's because it was allocated on the heap. Let me kick this down a notch. Actually, I should have put n over here as well. Let me kick this down a notch to only 10 and show you the visualization over here in Python Tutor. All right? I'll do it in that create array function, and let's visualize that execution. Now remember, it is not going to be allocated on the stack anymore. Now that we're paying more attention here and we know stacks and heaps, I can see that, oh, there's a heap over here. Let's go ahead and go next, next, next. See that? The array is pointing to this heap over here that's of size 10. That was still too big. I don't want to do all that. Fast forward, fast forward. There we go. Now, when I return back from this function, what's going to get destroyed? The stack frame is going to get destroyed. But is the thing on the heap going to get destroyed? Nope. But something still bad is going to happen. 3, 2, 1. Well, it didn't get destroyed. It just got lost. Right? It's basically my pointer here, my reference to this memory location over here, is now lost because it was destroyed in the stack frame. But this thing over here in the heap still exists. Right? This is known as a memory leak. Right? So if you've ever heard of this before, that memory is a resource, right? It's yesterday I talked about, I liken these things to toys. All right, so you get out your toys, right? And what do you do with them after you're done playing with them? What should you do with your toys when you're done playing with them? Put them back, right? Clean up. What if you don't? You leave all your toys on the floor. Nobody else can. You're hoarding your toys, basically. Nobody else can play with them. Nobody else can use them, right? You start hoarding and hoarding, and you hoard enough, and everybody else runs out of toys to play with, right? Not a great situation. Now, think of that as memory. If I've got a long-running program that runs for hours and hours and hours, always takes more memory, never gives it back, never cleans up after themselves, right? What's going to eventually happen? You run out of memory, or you reach your limits and the operating system says, no, you can't have any more memory. Or it just keeps happening and nobody can use this memory, and eventually everything grinds to a halt because you start running out of memory, you start thrashing, et cetera, right? So we need to clean up after ourselves, okay? And we'll talk about that here with memory management in a second, right? Upon success, malloc will return a pointer to the chunk of memory that it's just created for you. What about failure? Say that you asked for way too much memory. Say that you asked for 50 petabytes of data, right? of memory. What is a petabyte, by the way? Oh, is it? Yes, it is. So it goes mega, giga, tera, then peta. What's after that? Is it zeta? I thought it was exa. Is it exa or zeta? I don't remember. Anyway, there ain't that much. There ain't that much memory, right? And it's probably beyond the 64-bit addressing at that point anyway. So it doesn't really matter. You can't ask for that much. So upon failure, malloc returns what? What do you think? So it's not going to be a segmentation fault because of the way that you approach error handling, right? What if inside malloc we said, oh, this is a failure, I'm just going to exit out of the program, right? That would be like you and your RGB values or whatever it was yesterday, deciding they gave me an RGB value that was beyond 255. I'm going to quit out of the program, right? That's not good error handling. Instead, you communicate that back to the calling function that I can't handle your RGB values because they're out of range. I can't handle your memory allocation because you asked for 50 exabytes, right? So how do I tell the calling function that a failure occurred? I need to return a pointer. So what kind of pointer tells you that don't use this? Right? There be dragons here. Right? Don't try to do anything with this. I heard it. Null. Right? So upon failure, malloc returns null, and you can check for that if you really want to. In practice, I've never actually seen, as long as you're asking for a reasonable amount of memory, I've never seen bad things happen with it. But of course, it's always possible. For example, can I ask for negative 40 bytes? Does that make any sense? Right. Still works though. Right. I don't know why, but let's go ahead and find out. Let's go ahead and put in a check here. If the array ends up being null, then I can print an error message here. Printf, error, unable to allocate memory, end the line. And let's see if that actually happened. Or if it, there, okay, so it did return null. I was getting away with it down here. I don't know why. Why would I be getting away with it? Let's do it explicitly. Now, Bret Hart should be coming out of the computer to knock me over the head. There we go. I dereferenced a null pointer. It was definitely null because this error message was printed. I dereferenced it, and I think that the compiler might have been compiling away that other part, or I was getting away with it somehow. Okay. Anyway, segmentation fault. You asked for something absurd that you can't have negative 40 bytes. Okay. When you receive the pointer, you should, and I emphasize should here, cast it to whatever type of pointer you wanted. If this were a double array, then I would need to make this into a double, this into a double, and what else do I need to make into a double? Size of double. What happens if I don't? Let me restore this back to 10. I want 10 doubles. How many bytes does a 10 doubles take? 8 each, so 80 total. But how many am I actually asking for here? 10 times 4, 40 bytes. Can you fit 80 bytes into 40 bytes? Nope. You will get garbage results and ultimately, hopefully, a segmentation fault. Right? So these all need to be doubles. Right? And then you can do with it whatever you want. Okay? And casting it to a double, if it's a double array, casting it to a char, if it's a char array, and now you're getting into strings, which is the next topic that we'll get into probably next week. Okay? All right. By default, no, just like any other variable, by default, no default values are defined in C. If you create a static array or a dynamic array, what could be in there to begin with? Right? Let's go ahead and test it. I'll make it reasonably large, and let me go all back to integers here too. I'll make it reasonably large, 100 integers here. And without setting them, let's just go ahead and go through that array and see what the contents of that array is. For int I equals 0, I is less than n, I plus plus. Our idiomatic for loop. Do we all remember what idioms are? Raining cats and dogs. All right, they're colloquial metaphors that if you are in the language, you understand what those metaphors mean, not the literal meaning, but you understand what the intent is, what the connotation is. Here, if I didn't have any other piece of code, if you just looked at this one for loop, you would probably assume that it had something to do with an array of size n, right? Just because it's so common. That's why I and n are okay variable names, because they are idiomatic, right? In general, single letter variable names, single character variable names, those are terrible, right? X, Y, Z, or A, B, C, unless you're doing, coordinate systems or coefficients to something like that. Variables should be named what they represent. This represents an index. So maybe a better variable name would be index, but it's so common to do this that we don't bother writing out the full word. It's probably a better variable name to say number of integers or size of my awesome array, whatever, right? But it is so common and so idiomatic that we simply use I and n, and that's perfectly fine. Okay? Printf %d, array sub %d is equal to %d and the line. Let's find out what's actually in there. What do you think is going to be in there? Random numbers. Oh, they're all zeros now. All right, we'll make you larger, and then we'll do it. Malloc, %d, all right, fine. Whoa, it's behaving even differently from what it was yesterday. Fine. Oh, wait, there, I saw one. Oh, no, that wasn't it. Darn it. Oh, come on, really? All right, fine. 99 times, well, 1,000 times out of 1,000 times, apparently it will end up being 0, but there's no guarantee on that, okay? And if this were a static array, it would definitely be different, okay? All right, what about in Java? Dynamic arrays in Java? You've probably seen them before because I think everybody has raised their hand at least once to see when I asked whether or not everybody's seen Java. So let's go ahead and do this in Java. First of all, are there any pointers in Java? Nope. So how do I do arrays? Can I do static arrays? Apparently not, because there is a compiler error here, right? You can't see it. Syntax error. You can't be 10. Oh, maybe it's because it needs a variable instead. Nope, still a compiler error. So what's the syntax for doing this? Folks who have had Java before. Equals new, ARR, or new what? It's an integer array, so it's new int, no, not new array, but the type of array, right? And the size goes in here. If you tried to do some other type, it's going to complain about that. Wait, you want an integer array, but you created a double array. No. Right? So int, there we go. There, is the equivalent in Java, right? No pointers, except, well, no implicit pointers here. You don't use star, you use the square brackets here. No size, no malloc. Instead, you use the new keyword. And then you specify the type and the size. Okay, yeah?
Okay, so why would we want to use a static array in C?
For very limited instances, for example, if you had, if you only had a few number of values and that's it. So for example, int first 10 primes, right? And I could use this syntax here, 2, 3, all right, first 5 primes. 2, 3, 5, 7, 11? There we go. There's a static array. I knew everything that I wanted to put into it. Syntactic sugar allows me to just write them all out and do it in one line without having to write a for loop to do it, etc. And I don't care about returning it, so it's going to get destroyed, and I don't have to, now I don't have to do any memory management because I'm guaranteed that it's small enough that it'll fit in the stack frame will be destroyed for me, and we're good to go. Some other use cases would be if you've got an array of only a few number of possibilities, kind of like an enumerated type. If you wanted to hold all the strings representing classes like freshman, sophomore, junior, senior, right? You can go ahead and use a static array for that. You can get something kind of like that in Java, I believe. You can use this similar syntax, I believe. 1, 2, 3, 4. You can do this in Java. And now you're not using the new keyword. This is not a static array, though. This is just syntactic sugar, and Java is still allocating it on the heap, not on the stack, I believe. I'm 99% sure of that. Go back to this, though. Okay. So no static arrays, only dynamic arrays, no malloc. You just use the new keyword, right? So come back over here. Let's put this in the notes. Java doesn't have malloc. Instead, you use the new keyword. And here's the example that I'll give you over here. If you want an array of doubles, well, then it's just double numbers is equal to new double and then the size of there, right? I already mentioned bookkeeping before. Now, bookkeeping in both languages is completely different. C has manual memory management. Right? It falls to you. I'm going to emphasize that. You, the programmer, to keep track of the size of an array you create. Pass that size to any function that you also pass the array to. And ultimately, when you're done playing with your toys, actually, it also falls to you to ensure that no illegal or undefined access occurs. If what I mean by that is if you create an array of size 10, what happens when you try to access index 50? Hopefully it's a segmentation fault. It could just be that, well, that's your memory. You can do with it what you want. Right? And so you start corrupting your own program's memory. Right? In which case it leads to undefined behavior. Your program probably spits out garbage results. If you try to access memory that doesn't belong to you or that doesn't exist, yes, hopefully that's a segmentation fault. But ultimately, it's undefined. Anything goes. Anything could happen. Right? And finally, it falls to you to, you need to make sure you clean up the memory when you are done with it. What that means is you need to give it back to the operating system. To give it back, you use the free function. Right? It frees the memory, right? You free it up and you free up the memory for other use. You give it back to the operating system The operating system might give it right back to you if you reallocate and call malloc again. In fact, that's most likely what's going to happen. But otherwise, it might end up saying, okay, well, I need that memory for another process. So thank you for freeing that up. I'm going to give that up over to this other process over here. Right? Once you free it, however, that memory no longer belongs to you. Attempts to access it are undefined behavior. So let's come back over here to our example, and we'll kick it down to 100 here, where I set all the elements. Now let's sum them up. Int sum. Same idiomatic for loop here, and I will say that the sum, instead of printing them out, I'll say sum is equal to sum plus array sub I. So now a couple of issues here before we actually run this. Can you predict some problems just by the way that I've written the code so far? Sum is equal to %d and the line sum. My first question would be, what's in sum as of line 14? What's in it right now? It could be 0. It could be 0, and like all likelihood it probably is. It could be garbage. It could be dead beef. Always initialize your variables. Now, sum plus 1, sum plus 2, plus 3, plus 4 is going to give me the value. It's not going to be garbage plus 1, garbage plus 2. Right? Garbage plus anything is going to be garbage. What else? Or this is not an issue, but it's a, why did you write all that crap? How can I, plus equals, oops, plus equals, and now that's shorter, just syntactic sugar. All right. Let's go ahead and compile this and see that it works. Oops. All the sums are 0. Oh, I never actually set them, sorry. Let's go ahead, okay, so I'll set them out, print them all. So array sub I is equal to, this is the original code I had that I thought I still had. There we go. Now it's going to be 1, 2, 3, 4, 5, 6, 7, oops. Okay, go back to honors. G, there we go. There, 1 through 100, and the sum is 50/50, 5,050. Okay. What if I freed it up? Right. Now, doing this properly should be done when I'm done using it. I've put stuff in there, I've summed them all up, and then I've printed them out. I'm done using it. At the end of my program, I'm going to free it. By the way, this is a simple program. If you don't free it here, it's okay. It's not a memory leak because the operating system will clean up after you. Right? But if you have a long running program, say like a web browser, imagine if a web browser, say like Firefox, that used to be notorious for this, had a memory leak. That every so often it took another megabyte and it hoarded it, right? And you did that every 10 minutes or so. But it was a long running process that you kept your browser open for hours on end. Eventually it grinds to a halt, right? And you don't want that. You want to make sure that you're being good stewards of your resources. So you don't just want to rely on the operating system to free things up for you. We'll talk about stewardship and ownership of memory here in a second. But the proper way of doing this is at the end. What if I did it before I was done with it? So I set all the values, I print them all out, I free it up, and then I try to sum up all the values again. Yeah, does that matter? I freed it up. If I give you something back, give something back to you, you're the operating system. If I gave that back to you, right? Does it belong to me anymore? No, it belongs back to the operating system. So hopefully, oh, okay, garbage. All right. I was hoping for a segmentation fault here because I gave it back, but I said, wait, I'm still using that, right? Well, then you shouldn't have freed it because maybe I'm going to go ahead and give it to somebody else, right? In this case, the operating system didn't give it to somebody else. And so it just said, okay, fine, you don't want it, whatever. I'll use it for other things, but it's still yours in some sense, but it's going to give you undefined behavior. In this case, just garbage values, right? What was it before? 50-50. What is it now? Not that. Whatever the hell that is. Right? Okay. What if I did it twice? In fact, I'll do it correctly down here and incorrectly up here. So I have memory. I give it back to you as an operating system, and then I give it back to you again. Right? Yeah, something like that, hopefully. Ah, there we go. Double free detected in some cache. You can't free something twice. You can't free something if it doesn't belong to you, right? I can't go into a bank and say, free money, right? It doesn't belong to me. I mean, you could do that out of your own account, but it's going to detect that. It's going to abort that operation. So kind of like a segmentation fault, but it's a little bit different error and a little bit different message, right? So you can't double free things, okay? Once freed, that memory no longer belongs to you. Attempts to free memory that doesn't belong to you are also undefined behavior, so you can't double free. Right? Failure to clean up after yourself may result in memory leaks. Right? And you will witness this in your lab next week if you do the C version. Let me just go ahead and give you a preview of what I mean there. Get rid of all this. Get rid of all this. There we go. I'll go with 1,000, so 4K, and I'll go into a while loop here, while n, I is less than n, so int I equals 0, and do this, oops, and there we go, all right. Yeah, there, okay. So tell me about what I'm doing here. I'm going into this while loop and I'm creating a new array of 1,000 integers, so about 4 bytes. Not that big of a deal. Then I go, oh, I guess this is an infinite loop, I++, that's what I meant, right? So I'm doing this 1,000 times. I get another 4 bytes, or 4 kilobytes, another 4 kilobytes, another 4 kilobytes. Am I freeing any of this stuff up? I'm not doing anything with it, granted, but this is a toy example. So I'm hoarding memory, right? And if I did this for, say, millions of times, right? 1 million times 1 million, so 4 megabytes times 1 million is how big? Now you're petabytes? No, that's terabytes now. So this is going to be 4 terabytes of memory that I'm wasting, okay? Well, let's see if I can even do it. It's going to take forever. Oh, good, it killed it, right? Why did it kill it? Because I asked for too much memory. So let's kick that down a notch, and let's only waste 4 megabytes here at most. It's going to be perfectly happy to do that for you, right? You just hoarded 4 megabytes for a very brief time, fine. What I'm going to show you is a tool called valgrind. Oops, oh no, which valgrind? It's right there. Oh, okay. You want this. There we go. All right. Valgrind is what's called a dynamic code analysis tool. What valgrind can do is you can give it a program, and then it can simulate the run of your program and monitor it for problems. So linters, you remember what linters are when you use the wall flag? Linters are things that can look at your code and find potential issues with it before you compile and run it. That's why it's called static analysis. It's static because it's pre-compilation. This is called dynamic analysis. Do not confuse dynamic and static in that context with dynamic and static arrays. They're different contexts, so they have different meanings. Kind of similar, but not really. This is a dynamic analysis tool. It will actually run your program and monitor it and look for problems that potentially are there. It found some problems. It definitely lost how many bytes? 4 million. Where did we get that 4 million? 1,000 times 1,000 integers times 4 bytes each. That is 4 million bytes that I just lost. Okay? Valgrind was able to see that because I simulated it, right? And it's telling me that that's a problem. You need to fix that. Now, if I had compiled this a little bit differently, don't worry about the G flag. We'll talk about that later. it would actually tell me where you lost them all. There we go. 1, 2, 3, there. Again, 4 million bytes, definitely lost. And where did you, okay. I think I need some additional commands to give me more verbose output, but it can tell you that you allocated it on line 50 and it was never freed. So maybe you want to look into where you should free that. Where should we free it here? Right after we're done. We'll go ahead and free the array. Right. Now let's go ahead and run it again, or compile it, and run it just by itself. And of course, same behavior. But now let's put it through valgrind. Valgrind is going to tell me nothing was lost. Right? Here's the heap summary. Right? Total usage heap, 1,000 allocations. Right? That's because I went into this loop. 1,000 frees, and you used ultimately 4 million bytes during this process, but you didn't lose any of it. You didn't have any memory leaks here. Right? This is a dynamic analysis tool. It can do a lot of other things, by the way. This is just one of the things that it's good at. You can also do, heat mapping and like, why is my program so inefficient? Where am I spending most of the time? And it can do it's called profiling, and it'll profile your program and say that 90% of your computation time is spent in this one function over here. Maybe you want to look at optimizing that one function to improve your performance. And these are all sorts of dynamic analysis tools that you can use. And you'll see it in your lab next week if you do the C version. You'll see it also if you do the Java version. Right? Even though you can't have memory leaks in Java, you can, even though there's no memory management. Right? So in Java, Java has no manual memory management. It is all taken care of for you by the garbage collector. And that's literally what it is. It's the garbage collector. If an array or an object or whatever is no longer in scope, nobody is using it, nobody can use it, then it becomes eligible for garbage collection. Right? At certain increments, the JVM will run on its own, the Java virtual machine, will run on its own and reclaim memory automatically. You don't need to worry about this, right? Mostly. There are ways that you can try to force the garbage collector to go out and do their job, but you don't want to. There are very sophisticated heuristics and algorithms at work here that you don't want to muck with. Not only that, but even if you try to force it to, the Java virtual machine will say, look, there's this chunk of memory over here that I could clean up, but here's how long it'll take me, and the cost is not worth the benefit. I'm not going to do it, right? Even though you told it to do it. Right? It's just going to say, I'll do it later. Right? It's a procrastinator. It's not actually a procrastinator. It just optimizes its work. Another thing to realize about Java is that there's no bookkeeping at all. Right? Instead, all you need is array.length, and that tells you how big the array is. Let's go over here to Java and look at it. Right? So, how would I write an idiomatic for loop here to iterate over the elements and set them? For int I equals 0, I is less than n. Well, I could do that because I'm doing my own bookkeeping here. But what if I don't have n? What if it's just 10? Now I don't have n. Oh, I could hard code 10 if you want to. But how else? Array dot length, I plus plus. And I can set the value at array sub I to be I plus 1. And I get the exact same behavior as before. Okay? So array.length relieves me of the need to even do bookkeeping. No memory management, no bookkeeping at all. However, arrays in Java suck. Don't use them. Right? So has anybody, those of you that have had Java before in their lives, you've used arrays before, yes? All right. And were you ever told, don't use them? Okay, good. Then I'm telling you something new here, right? Why not? Why don't you want to use them? Because there's stuff that's so much better. Right? There are these collections, right? In Java, regular old arrays are terrible. there are much better collections called dynamic data structures. In fact, when you get to Computer Science 3, I call it Computer Science 3, but the official title is Data Structures and Algorithms, right? We like data structures because, one, we like data. That's our whole purpose for existing as computer scientists. Now we've got a bunch of other people trying to encroach on our area and call themselves data scientists, right? No, we're the data scientists. We're the computer scientists, right? Anyway, you've got data and you've got structures. We like structure because structure can be exploited for efficiency. Right? How can we exploit structure in this case? We can have dynamically sized lists for one. Right? Lists are ordered collections that use zero indexing, right? Just like arrays, but they grow and shrink dynamically and automatically as you put stuff in and take stuff out. Right? Awesome. If you create an array, even a dynamically allocated array, that array, size 10 say, that array can never hold more than 10 elements. It can hold only 5 elements, in which case you're just wasting the rest of the memory. Right? It can hold 0 elements, but it will only ever have a fixed capacity. If you need to add an 11th element, you need to create an entirely new array. With a list, you don't have to. Right? So let me come over here to Java and show you a much better way of doing this. Forget you arrays. Let's go ahead and create a list of integers. Right? And I'll call it, instead of ARR, I'll call it my list. Right? Equals new list of integers. There we go. All right. Now, of course, I'm going to need to import these. There are several libraries with a list class. Make sure that you are bringing in the right one. Java.utils, come on, expand. Java.util list is what you want. You don't want the AWT list. You don't want some random list out there. Right? You want the Java.util list. All right, so those of you that had Java before, you've seen lists? Okay, a few of you, all right. Don't use arrays when you got lists, right? Why drive a broken down Chevy when you've got a Lamborghini? Yeah.
What about like an array list?
Okay, good. That's actually why it's not compiling here. A list is a generic notion of a collection. It's an ordered collection. There's a first element, there's a second element, there's a third element, and it uses 0 indexing, right? And then there's a last element. They're not all necessarily contiguously allocated. It depends on the type of list. But you can't just create a generic list because a list is just an abstract concept. You can create an array list. As the name suggests, under the hood, there is indeed an array there being supported. But you don't have to worry about it, right? Let me go ahead and import this. That's also in the utils library. Java.utils. Come on. All right, fine. I'll do it automatically, manually, I guess. Array list. There we go. Oh, because I erased that array list. There. Now it compiles. Okay. Of course, we still got a problem down here. Now, let's walk through this. The list is just the generic idea of a list. What do you want to put in your list? I want to put integers in my list. This langle-wrangle, that's called a parameterization. It says that this list is only good for integers. If I wanted a double list, what would I end up doing? Double. What if I wanted a student list, a list of student objects? Student, right? We haven't created our own objects yet, but we will eventually. Let's just go ahead and stick with integer for now, okay? I'm going to call it my list. Right? And I still use that new keyword because I want to create a new list. What kind of a list do you want? Do you want an array list, or there's this other thing called we won't get into it, but a linked list, right? That represents the list elements a little bit differently. We'll just go ahead and stick with array lists for now. Now in old school Java, you would have to repeat your type over here, right, this parameterization. As of at least 15 years ago, you don't have to do that though. Right? So this parentheses right here is called it's calling what's called a constructor. Again, I don't want to get into it yet. Just know that this is how you can create a list. Right? Once you've gotten a list, you can do a lot of things with it. You can go mylist.add 10, mylist.add 20 and 30. So what does the list look like right now? If I were to print it out, system.out.println mylist 10, 20, and 30, because that's the way that you added stuff to them. That always adds to the end. What if I wanted to add at the beginning? Mylist.add at index 0, the value 42. And let's print it out again. If I were to do this with an array, what would I have to do? I'd have to shift everything down to make room for it and then put it in there. But the list class takes care of all that stuff for me. Right? Again, broken down Chevy versus your Lamborghini here. Right? I don't know, you might prefer a Chevy. Right? Anybody prefer a Chevy over a Lamborghini? Right. Well, if it's your own money, then sure. Oh, yeah, yes? Oh, okay. All right, well, then whatever sports car is good. Corvette? Okay, Corvette. All right, what else can I do? I can take things out. Mylist.remove the element at 0. The 42 that I just put in, let me remove something else. Let me remove the second element instead and print it out. 10 is now removed. Cool, right? What if I wanted to? What if I just wanted to iterate over them? For int I equals 0, I is less than. Now array.length. That's how you do with arrays. How do you do it with lists? Size. Right? There is no .length with a list. I plus plus. How do I get? Oops. How do I get the ith element? Just .get. Right. So system.out.println mylist.get the ith element. Cool? Yeah, go ahead.
So in C, size is not a method, but in this case, size is a size method.
Yes, it is a method. And technically, .length is not a method. It is a property, and it is pretty much only with arrays. Arrays are in a limbo between whether or not they're a class or a thing, and it's just a hackish way of doing it. That's yet another reason to use lists. Yeah, go ahead.
Is there no need to use quotation marks in the print line?
No, because it's println. It's not printf. If it were printf, yes, I would need to do that. Yeah.
So if you wanted to use this to iterate additions to the list, would it keep getting updated in size and just infinitely rotated?
Yes.
Okay.
Well, no. I take that. Let's find out. Mylist.add 101. I think that it would get. I'm always adding 101. Actually, I'm thinking that this is going to be a fast fail concurrent modification exception. Concurrent modification exception because I want to be right. Nope. Okay. Darn it. I'm wrong. So yes, this is an infinite loop because you're always adding 101. The size always gets updated. What I was hoping for there was something called a concurrent modification exception, which means that if you are iterating over a collection and changing the collection as you go, or changing something that makes it bigger or smaller, you're basically pulling the rug out from under the operation that's iterating over it. Java can detect that and then throw a concurrent modification exception and resulting in a killing of your program. In fact, I think I can force it with what I was going to show you as the last thing here. So arrays, old, broken. Lists, new, shiny, right? And they're hardly new. They're as old as Java is. But also, idiomatic for loops like this. Old, broken. Let's take a look at a new, shiny. This is called a for each loop, even though it doesn't use a for each keyword. For each integer x in the collection mylist. If you don't care about the index, you can simply just use this Java calls it an enhanced for loop. It really is just a for each loop. In fact, the way that I read this is, for each integer x in the collection or in the list, my list, do something here. X will get updated on each iteration automatically, right? And this is a colon, not a semicolon. That's the syntax for doing this. This will run for, oh, all right. Stop. Right. There we go. This will run perfectly fine now that I fixed that, right? You can see that we iterated it over once with the regular the old broken for loop here, and this new shiny for loop here, that we did it again. Right. Now let's try. I think I'd say 75% sure that this is now going to be a concurrent modification exception. If I try to add within an enhanced for loop, dot add 101. Come on, come on, come on. Yes, excellent. Concurrent modification exception. Right? You used an enhanced for loop, which means that it created this object called an iterator that then went over each element in the list, 42, 20, 30. But while you were doing that, while you were walking on the carpet, somebody pulled the carpet out from under that iterator. The iterator saw that the carpet was being pulled out from under them and said, nope, we're not doing this. I'm going to throw this concurrent modification error. And check for co-modification is what it's doing. And I asked for the next integer in that list. It says, okay, before I give that to you, I'm going to check, has anybody screwed up my list here? Has anybody screwed this up? If so, yes, you added 101 to it. Okay, throw this exception. Right? And so if you do it with a traditional for loop here, no, because you're not asking for the next. You are saying, give me the ith one, give me the ith plus 1th one, give me the third one, right? And you're never, and so that check is never actually run. And that's why it went into an infinite loop up here, but a concurrent modification exception down here. Right? So that is just the tip of the iceberg. You also have things that are called sets of, say, doubles, right? Numbers. Right? You also have the most powerful of all, maps, where you can map one type of object to another type of object. You can map integers to strings. All right? So we'll take a look at both of those later on. The only difference here is set. A set. Does anybody have experience with sets in math? What is a set? A set is a collection of unique objects. So with a list, I could have 10, 10, 10, 10, 10. With a set, you can only have 1 10. Any duplicates get rejected. And it's unordered. So iterating over it, there is no first element, there is no second element, there is no third element. There's just this bag of elements. The map, again, can map any arbitrary object to any other arbitrary object. So you can map integers to strings, strings to strings, strings to integers. You can map integers to integers, whatever. Any object to any object. And this is a key and a value. And it's way more powerful than either a list or an array could ever hope to be. And we'll look at those when we come back on Tuesday. Yeah?
So when we declared the list at the top, is there a reason that we, like, the first declaration is just a list and then the second one's a row?
Yeah, because this is what's called an interface. All it does is it defines the methods of the class. It doesn't actually define the definitions. It's kind of like the prototypes without the definitions in C. An array list has both. Right? It conforms to the interface. In other words, this add method, the list says you have to, if you're a list, you have to have this add method. If you're a list, you have to have this remove method. Right? Well, I'm a list, and I implement this add method by doing X, Y, Z. Right? I implement this remove method by doing X, Y, Z. Right? So these are the array list is an implementation. This is just an abstract idea of what a list is. What is a list? Well, a list is something that has an add method and a remove method, among other things. But it doesn't actually define how those are executed. The array list does. Right? And that's all object-oriented programming, inheritance, and abstraction next semester. You don't need to know any of that in order to use the tools now. All right.
The array
It's a hierarchy. A list is actually an interface, and then the array list. Then there's actually several things in between. There's an abstract list. There's a collection. There's an abstract collection. There's an abstract list, and then finally you get down to an array list. So there's a whole hierarchy there.